let's talk about, I'm going to call it weak calibration. And what I mean by that is we're just assuming that we've got two projective cameras so that they're going to behave like projected cameras, but in particular we don't know anything about focal length or their offsets. But we are going to assume, for example, that we don't have radial distortion. We're going to assume that we don't have a non-uniform stretch of the image. So, but when it's, say, weakly calibrated, that's all we mean. We correct for that. So the main idea is that we're going to estimate the epipolar geometry from a set of corresponding points between uncalibrated camera images. And we'll probably use a large set, so it's going to be somewhat redundant in order to make this thing more robust with respect to noise. All right, so let's get started. So before, from our all our projection stuff, you'll remember that we had this projection that went from a world coordinate through our extrinsics to our intrinsics to a projective representation of the image coordinate, right? And so to get the non-homogeneous, you had to divide through. So it's written here like it's a scale, W times the image point is equal to the world point times our extrinsics times our intrinsics. So phi is just as we did before. We're going to use a 3x4 version here since K will be a 3x3, where the left-hand side is that rotation matrix and the right-hand side is the transformed translation. And you'll notice a slightly weird form written here of it's R times T. And all that's saying is that if you know the translation in one frame, you might have to translate, you might have to express it in the other frame depending exactly on how you're doing this. Don't worry about that detail. Okay? So that's phi, our extrinsic parameter matrix. And K, if you remember, that's our intrinsic calibration matrix. And the K that I'm showing you here has a focal length and an X scale and a Y scale. And of course, as we said before, they're multiplied together. You really only need two numbers. You've got F divided by SX and F divided by SY, so they always appear as multiples like that. But we have a scale in both directions. We have the offsets, but what we don't have is we don't have any skew. That is that this value here is 0. That makes this math a little bit easier, and as I said before, in general, for modern cameras, skew just isn't an issue. All right, so I'm going to write that this way. The point in the image, and this is a homogeneous point, is the point in the world times our multiplied by the extrinsic matrix multiplied by the intrinsic matrix. But this, of course, is just the world point put through the extrinsics. That is the location of the point. It's a 3D point, but it's in the camera frame. Remember that the extrinsic matrix maps us from some arbitrary world frame into the 3D frame of the camera. Okay, so that we're going to call that PC. And so we can write down this very simple relationship that K, the intrinsics here, maps us from the point in the camera coordinate system to the homogeneous point in the image. Okay, so P in the image is equal to K intrinsics times P in the world. It's the point in the world, but expressed in the camera frame.